So, thank you very much. Professor Quark is a wonderful host, so I feel very welcome here. So, what graded Betti numbers can tell us, as you said, this is a Germanism. It should read, what can graded Betti number tell us? That's maybe. So, it all started out with Hilbert's syzygy theorem. So I have a polynomial ring in n+1 variables. I normally think of this ring being the homogeneous coordinate ring of a projective space. So it's standard graded, and I have a finitely graded S module, so which graded pieces I denote by MD. Then the basic theorem of Hilbert, which started in my eyes homological algebra, is that M has a finite free resolution. So to specify a module over a ring, one way is to give generators and relations. So F0 and these Fi are free modules. Direct sum of S, well, I should keep track of the degrees of the generator, so there will be beta I generators in degree J. So these are free modules, so F0, F1. Here, the map between these three modules is simply a matrix, and we can think of this first matrix as giving the module M via generators and relations. Now, of course, free modules are much simpler than arbitrary modules, and so we can think of the kernel of the map from F0 to M1 to be another module, which again has a presentation. So we have a map from F1 to F2, and we can repeat this. And the fundamental observation of Hilbert was that if we repeat this and we choose, say, at each step, say, a minimal number of generators, then this process stops. Finally, we get inclusion of the last map. So these are all free modules, and the sequence is exact, which means that in each step, so the co-kernel of the map from F1 to F0, that is M, and the kernel of the map F0 to F1 would be the F2, which I didn't write down here. So he proved this result. Why was he interested in this? His main motivation was to prove the polynomial nature of the Hilbert function. So we have this free resolution. Here are the generators. The Hilbert function is the function which associates to the module the dimension of the graded pieces of the module. So for each D we have a graded piece, we have its dimension, and we would like to have a formula for this dimension. It will be formula involving D, and since this is an exact sequence, it will be exact in each degree D, and in each degree D, this will be finite dimensional vector spaces. So we have an exact sequence of finite dimensional vector spaces, and then the alternating sum of exact sequences of dimensions of exact sequences of vector spaces, this is always 0. So I have this formula here, and well, I do know how many elements of degree D I have in this free module. So I have D plus n minus j, because I have a twist minus j over n in sort of Sj. I have beta ij copies of those, so this is the formula. And now, as Hilbert observed, this can be interpreted as a polynomial in D, if instead of the binomial coefficient I write the polynomial, so d plus n minus g times d plus n minus g minus 1 and so on, divided by n factorial. So this is a polynomial. All right, so we have and equality holds if d is sufficiently large. So the Hilbert function is computed by a polynomial if in large degrees. An equivalent formulation which people frequently use, if you have a sequence of numbers like dimension of m, k, md, you form the generating function. This is called the Hilbert series. So formally, at this point, this is sort of a power series in T Well, D might also, M might also some stuff in negative degree, but it's finitely general, there will be not so much, so only finitely many terms, so it's a Laurent power series. Right? And this can be expressed in the following way. I have here the Hilbert numerator divided by 1 minus t to the number of variable. It's actually this formal power series is actually a rational function. And that's basically equivalent because the Hilbert series of S or S minus J is sort of given by, well, this is this definition, but it's also given by that power series. If you expand this into a power series around the origin, you get this series here. So that was Hilbert's motivation. I should give him one example. There's a twisted cubic, so I embed P1 into P3 by taking homogeneous coordinate St to homogeneous coordinate S3 to S squared T S T squared T cubed. And it's not hard to see that these equations are satisfied. So x1, which is this here, this to the square is equal to that times that. That's the first equation. Then the second equation is this times this is equal to that times that. And the third equation is similar. So this squared is that times that. And so these are elements in the ideal, and it's not too hard to see, but it amounts to a little bit of a computation or thinking that this is all the relations. So the presentation is given by this matrix, and the kernel is actually in this current term case free. It's generated by this nice matrix. And let me point out one peculiarity of this matrix. If you take this minor here, x1 squared minus x0, x2, it occurs here in the equations. Similarly, the other minors show up in the equations. All right. So Betti numbers and Betti tables. Well, the Betti numbers are these beta ij. So I have this free resolution. And I'm going to collect this beta ij in a table. So in position 1, 1, I put beta 1, 2. The total degree is 2, 1 plus 1. So in the example of the twisted cubic, we had 3 quadratic equations and 2 linear relations among the quadrics. So a way I sort of think, this is in a line. These 2 numbers stand in a line. This stands for a linear map. These 2 numbers stand in a square, right? So this is a quadratic map. Well, the minimal resolution, the one which I choose if it, do they tell us? Well, the basic information which we can get, so now I specify to the case that M is a variety, X is a variety and M is a homogeneous coordinate ring. Then of course it's generated by one element, the quotient of S. So there's one generator here. And the non-zero entries maybe are in this box. So this is the length of the resolution C, and this is sort of the height of the table R. So then we do know what the length of the resolution will be. It's sort of C is sort of the number of variables minus the depth of the module M in the homogeneous maximal ideal, and that's always larger or equal to the codimension. It's nice if equality holds. In that case, one calls the module Cohen-Macaulay. R is the regularity. This is basically the definition of the regularity, the Castelnuovo-Mumford regularity, where, yeah. Then the Hilbert polynomial, we can, which is determined by these Betti numbers through the formula, has degree equal to m the dimension of x. And it's actually an Euler character. So Px of S is the Euler characteristic of the structure sheaf of S. So it's a polynomial of degree m, S to the n, plus lower order terms. And the leading coefficient is the degree of x divided by m factorial. So the degree of x is, of course, the number of points a complementary dimensional hyperplane will intersect the variety. And let me point out that one of the important questions which is whether we can bound the regularity in terms of the degree of X. And Professor Quack did important work in this direction, which I'm not going to report today. I hope you all know this important work. Well, there's also a version where I can sort of get the formula for the dimension or for the codimension. The Hilbert numerator is divisible by 1 minus t, which was the denominator or a factor of the denominator, with multiplicity precisely codimension of x. So we can read off the dimension from these Betti numbers, or the codimension of these from the Betti numbers. So if you go, let's do small examples. So first, small codimensions. If c equals 1, then x in Pn is a hypersurface, is defined by a single equation, and we just have sort of a very short resolution, just 2 terms. If c is equal to 2, if the codimension is 2, then the length of the resolution is at most 2. And the rank of these 3 modules, f1, f2, differ by the rank of this module. So rank of f1 will be rank of f2 plus 1. And the second map, which is sort of given here, is given by an k plus 1 k matrix, where k is the rank of f2, which are called phi ij. And the first map, that's a sort of the discovery of Hilbert, which was rediscovered by Birch, is given by the minor. So I have a k plus 1 times k matrix. I can drop 1 minor, so I let I not equal to L. Now this is a square matrix. I can detect the determinant and take that delta L up to sign. This is the determinant. So why is this a complex? Well, that's basically Cramer's rule. So I have here a k plus 1 times k matrix, repeat one row, one column, the jth column, and expand it. Then on one hand side, I get, if I expand with respect to this row, I get the coefficients phi I j, and the complementary minus will be just the delta I with the right sign. I put on the right sign. On the other hand, of course, the determinant of this matrix is equal to 0 because I have repeated a row. So delta and phi define a complex, and it's going to be an exact complex if the delta I defines something of codimension 2. So what about the next case? We have the famous structure theorem of Buchsbaum-Eisenbud. So if the codimension is 3 and I have an additional assumption that xx is Gorenstein, this means 2 things. One thing, it means that the projective dimension, which is 3, is equal to the codimension. So we're in the nice case of equality in the Auslander-Buchsbaum-Serf formula. And the second one, that's symmetric. So here is rank 1, here is also rank 1, then f1 and f2 must have equal rank. And actually the whole resolution is symmetric with respect to dualizing into Hom S minus S. So if I take the transpose matrix, I get basically the same matrix back. Actually, the middle. So then the first discovery of Buchsbaum-Eisenbud is that the rank of these 2 free modules, which are equal, is an odd number. So it's say 2k plus 1, and the matrix is symmetric, and then the first and the last matrix are given by the 2 by 2 principal Pfaffians of phi up to sign. So it's sort of very similar to the first case. Only the middle matrix is sort of has to be given. The other matrices depend only on the middle matrix by a formula. So to give you an example, if I take the Grassmannian G25 in P9, its Betti numbers are 1, 5, 5, 1. So there's a linear matrix, a 5 by 5 linear matrix. I say it's skew. So, and the Pfaffians, which are Pfaffians of 4 by 4 matrices, so the square root of a 4 by 4 matrix of linear entries, this is a quadric, so there are 5 quadrics, and the resolution is here. So in the middle, actually, it's just a generic skew-symmetric matrix. Not too surprising if you think of G25, and here's the resolution. The other thing which we could now, we look at small dimensions, so maybe curves, or maybe even very special curves, canonical curves. So C is a smooth projective curve over the complex numbers of a genus G. Then there are G holomorphic differentials, omega 1 up to omega G. And the map which sends C to the Pg minus 1, the point P, to the ratio of the values of this differential at that point is an embedding unless C is hyperelliptic. And then we have the theorem of Max-Noether that if C is not hyperelliptic, then the homogeneous coordinating SC of C is Cohen-Macaulay. Let's remember that the projective dimensions of the length of the free resolution of the coordinate ring is equal to the codimension, which is G minus 2. So for the next few minutes, I will talk about what these Betti numbers can, how do they look like for canonical curves. So, of course, we can compute the Hilbert polynomial of a canonical curve. The degree is 2g minus 2, and so the Hilbert polynomial takes the form 2g minus 2 plus 1 minus g. This is sort of reminiscence of Riemann-Roch. If you think about this in Euler characters, you would expect that the formula should be written that with this, and that we don't, that we sort of write the constant coefficient as 1 minus g is sort of for historical reasons. So here are the Betti tables of canonical curves of genus 7 over a field of characteristic 0. So the surprising thing, there are only 4 possibilities. This is a general case. Here the numbers are a little bit larger. Let's jump up by 3. And we have a orthogonal curve. So a general curve of genus 7 can be written as a 5-to-1 cover of P1, but special curves are 4-to-1 cover, so they are the orthogonal curves. And if we have a orthogonal curve, we have extra syzygies at this spot. Then these curves have a map to the plane of degree 6. So if it's a plane curve of degree 6, then it will actually have 3 G1-4s, because the plane curve will have 4 nodes, 3 nodes, and the projection from the nodes defines a function of degree 4. So 9 is actually 3 times 3, so that sort of makes sense. And then we have the trigonal curve. The surprising thing is that sort of no other numbers are possible. For example, why can't we have here a 1? I should point out a few more facts. You see that the difference along the diagonal is always the same. This only depends on the Hilbert function. So 20 minus 4 is 16. Well, here these numbers have to be equal, right? They're always equal. This comes out easily from the formula relating the Hilbert function to the Betti table. It's Gorenstein, so that's there's some symmetry. So we have in the end a 1, and the numbers are actually symmetric to that point, right? It's symmetric. So that is all very easy. What's not so easy is to understand why can't you have say a 3 or 2 or 1. And indeed you can have their different numbers if you drop the assumption smooth. So if you allow reducible curves, then more tables are possible, and it's more difficult to classify them. This was for curves over the complex numbers. If we go to curves over arbitrary fields, there's one difference. If we have a field of characteristic 2, then we get here an extra syzygy which doesn't have sort of a nice geometric interpretation so far. All right. So what's the general picture? Well, it's Green's conjecture from 1984. So C and Pg-1 are smooth canonical curves. Then the Betti number B P plus 2. So there's a Betti in the second row is non-zero if and only if there exists a linear system of divisors of dimension r and degree d, d less than g, such that d minus 2r is less than equal to p. So one direction was proved by Green-Lazarsfeld. So if you have a special divisor, you get some geometry. Out of the geometry, you get that this number is non-zero. The case P equal to 0, you might think of Max-Noether's theorem. The case P equal 1, so you have the canonical curve is not defined by quadrics alone, so you need quadrics and cubics. That was settled by Petri. He proved that this can only occur if the curve is either trigonal or isomorphic to smooth plane quintic, and the case P equal to 2 is completely understood by work of myself and Claire Vazon. So here are two very nice results. This theorem of Vazon is really a highlight in syzygy's theory. She proved that the Green's conjecture holds for the general curve of genus G. And starting from that, with the help of Hershowitz and Ramanan's result, Aprodo and Farkas could prove that the Green's conjecture holds for smooth curves on arbitrary KC surfaces. Of course, all only in characteristic 0, because in characteristic 2, as I showed you above, that's not true. So this is for two reasons a difficult theorem. For one, there's a special assumption that we have characteristic 0, which we have to use at some point. And yeah. On the other, it was for a long, long time open. So this Green's conjecture was in 84, and for 2002 or 2005, it finally was settled for the odd genus curves. So let me change gears. Which Betti tables can occur? I could ask this for canonical curve, and I'm completely sure that I will not live to the point where somebody tells me the answer. I don't think that this is really possible. It's too complicated. I would like to put this in a more general framework, which Betti tables at all can occur. And well, I cannot expect, if I ask it more generally, to have an answer. But the amazing thing is that if you allow a simplification of this question, has a complete answer. So for the rest of that, I'm going to explain that. So the basic observation, which is completely trivial, is if you have two graded modules m and n, and you take the Betti table of the direct sum, then it's the sum of the Betti tables, well, maybe sort in the space of all tables. So if I can go from 0 to n plus 1, in J, this was a generator of the degree, can be arbitrary in Z, but it's a finite table, so it's a point in this vector space. So we define the Bo-Soderborg cone as a rational cone generated by Betti tables of graded modules over with positive rational integers. So I take linear combination of these Betti tables with rational coefficients. So this sits inside this vector space. And as I said, for the rest of the talk, I will give a complete description of the Bo-Soderborg cone in terms of extremal rays. So pure modules. An S module is called pure if it has a nice property that's Cohn-Macaulay. Recall that means that the projective dimension, the C, is equal to the codimension. And secondly, in the minimal free resolution, where normally I have many generators of different degrees, I only have generators in a single degree di. So I simplify the beta I notation. Here should be beta I comma di. I dropped the second index. So the minimal resolution is pure. So in each term I just have one degree occurring, and the degrees which occur are called the degree sequence. And so we have d0, d1 up to dc, and this specifies the degrees which occur. What about the numbers? Well, here's the proposition. The Betti table of a pure module spans an extremal ray of a Bo-Soderborg cone. So we have that the Hilbert numerator, which is this sum now. I have no sum over j anymore because there's only one j. And its first c derivatives vanish as t equal 1. This was because 1 minus t to the c divides this. This gives, if I differentiate, c linear equations for the c plus 1 coefficients beta I. And the equations, well, if I differentiate, I get in di. If I differentiate again, I get sort of in di times di minus 1. So basically, the system of equation which you get is a fundamental type. So it has a unique solution up to scalar. Thus, the beta I are uniquely determined by the degree sequence up to a scalar. And if you think about this, this is basically saying that beta m is an extreme array. So this is one of the main results of Bo Soderborg theory, a theorem together with Eisenbud, and then of course Bo Soderborg, who sort of got the idea that such a theorem could be true. The Bo Soderborg cone spans of Betti tables of pure modules. Thus, what we get, thus given a table of non-negative integers beta, with entries beta ij, we can decide whether it exists in R, an integer greater than 0, and a module M, such R times the table is a Betti table of a module. So that is a thing which we can decide. We cannot decide whether beta is a Betti table itself, but a multiple of beta, whether that is a Betti table of a module, can be decided. And the module actually explicitly constructed. So how does this decision process go? So here's an algorithm. It's a greedy algorithm which decides whether a Betti table occurs. So the algorithm will answer this question whether beta is in the Bo Soderborg cone. So input, of course, is the table, and output will be yes or no. So first, I define d0 up to dc by taking the smallest beta j for which beta ij is non-equal to 0 for each I. So this defines the di's. Now, if this sequence is not increasing, then there can't exist such a module, and the answer will be no. Otherwise, I take a pure module with that degree sequences and consider the smallest integral point on the ray corresponding to that module, and compute the largest rational number gamma greater equal to 0, such that the beta prime, which is beta minus gamma, this number has non-negative entry still. So that it subtract too much, of course, some of the entries will get negative. I just sort of make one of these beta ij's primes will be 0. If beta prime is equal to 0, then we terminate with yes, then it is, and otherwise we take this table as a new input in 1 and repeat the procedure. So we subtract, and see whether we this condition 2 is always satisfied. So here is an example. I take the Betti table 1551. The degree sequence is this. The corresponding Betti table, the smallest integral value of this is 1, 10, 15, 6. I want to subtract that. So I can at most subtract a 6, because 6 divided by 6 is 1. So then if I subtract that, this number is going to, in this position, will be 0. And the remaining part actually is then sort of a multiple of this Betti table, 6. So yes, this is inside the Bo Soderborg cone. Another table. So I just sort of move this table a little bit. I have larger numbers here, 6, 6, and then a 1. Here the table has this term, and it can subtract in half. And in half of this will do, for example, half times 9. 9 halves plus 3 halves are 12 halves, which gives 6. Here's an example which is sort of of a pure module right away. So this is actually one of the Buchsbaum-Eisenbud codimension 3 Gorenstein examples. So here this matrix is a 7 by 7 skew symmetric matrix, and I take this 3 by 3 and 6 by 6 fashion with the cubics, and that will be the solution. And here, the next case here is, well, I go one step further. So here, if I subtract something, so the corresponding Betti table which I have to subtract is this one, and I can subtract at most the fifth. But then I get 0 here, so if I take the infimum, then the first d0 will be plus infinity, which is larger than 3. So this is no longer in the, I get answer no, this is not in the Bo Soderborg cone. So I think I was too fast. I'm finished now. No, not. I want to. Good. So Bo Soderborg theory says a lot about the relative values beta ij divided by beta 0, 0, right? Because it says something about the scalar multiple, only up to scalar multiple. So the biggest missing piece of information are lower bound for the absolute size of this number. So here is another famous conjecture of Buchsbaum-Eisenbud and Horrocks. So if M is a graded S module of codimension C and beta M is Betti table, then the sum of the Betti ij's, the rank of the j's module, is at least C choose I. In particular, if I sum over all the Betti tables, all the Betti numbers, it's 2 to the C. It's greater or equal to 2 to the C. So that's the lower bound. So we would like to have a lower bound on the size, and this is a long-standing conjecture which was only proved in very few special cases. So here's an example. This is in the Bo Soderborg cone, but it's not the Betti table of a module, because 2, which is sort of, the codimension is 3, so 2 is smaller than 3. So it's not the Betti table of a module, but twice it is. So if I multiply by 2 this table, I get 2, 4, 4, 2, and that is a Betti table of a module. If I take a generic 2 by 4 matrix and compute its resolution, the resolution of the co-kernel, it actually will have this shape. So this is indeed a Betti table, and I conclude with this important question. Prove this. Prove the Buchsbaum-Eisenbud-Horrocks conjecture. That would be sort of a major breakthrough in syzygy theory and Betti tables. Thank you very much.